Okay. I would like to thank the organizers for inviting me to this conference, and I would like to apologize for breaking the symmetry in the topic of this average topic of this meeting, for which I need to compensate with not such a massless introduction. Okay. So to start with, I would like to acknowledge my collaboration. This work was done with Professor George Sawatsky from UBC in Vancouver, and in India, it's funded by this DST project. Okay, so 3D electrons in transition metals are special. They are highly correlated because, as you can see, the radial extent of the 3D wave function is much smaller compared to S and P. So whereas these can be easily modeled using band theory, the 3D electrons do not, are not easily modeled by band theory alone. So the most prototypical model to describe these compounds is this Hubbard model, which most of you are aware of. So part of this is the simple tight binding model, which gives you a band of width 2zt, where z is the coordination number. To that you add this term of pairing. So basically, so the repulsion between electron pairs at the same site. So think of this as a hydrogen atom lattice, and this is the price you pay if two electrons are at the same site. Now, a more formal or general way to define this is the following. So you take this configuration where every site is filled with one electron, and now you take out electron from this site and place it at a very far away site, creating an empty holon and a doublon pair, but separated a lot in space so that you don't have excitonic effects. So the first process is ionization, electron ionization, and this is electron affinity. So the Hubbard U is basically the difference between these two and is given by these, the energy difference between this in a combination actually here. Okay. Now, when you introduce the Hubbard model, you no longer have such a simple picture. So it splits into these quasi-particle bands, the upper Hubbard band and the lower Hubbard band, which is separated by U, like I was showing you. Each of these, of course, has the same kind of bandwidth W. Now, depending on the relative strength of U or W, you could either have a Mott insulating phase when U is larger than W, or you could have a correlated metal when these things overlap. The strong correlation case is the pathological case where U and W are of the same order of magnitude, so that you have no small parameter in doing perturbation theory. Okay. Now, life is not that simple. You don't always work with elements. So when you go to transition metal compounds, on the other hand, you need to introduce ligands or oxygen, for example, oxides like lanthanum cobaltate, LaCO3, which I'm going to talk about. You also have a band which is this oxygen band. Okay. Now, this energy difference between the oxygen band and the upper Hubbard band, this excitation energy is called the charge transfer energy. Now, that is the energy between these two configurations where you have n+1 electrons on the, so you basically have n electrons to start with on the transition metal, then you excite one electron to the ligand and create a hole here. So that is given in terms of the on-site energy differences as well as a certain multiplicative factor of the Hubbard U. Now, based on this, we have classified, I mean, it has been classified in literature that when delta is much larger than U, you have the classic Mott Hubbard insulator, where the oxygen band is not in between these. And of course, the doped holes and electrons both have D character. On the other hand, when you have the oxygen band lying in between these, the basic energy excitation scale is from this band, oxygen band, to the upper Hubbard band. Now the doped holes have ligand character. This is called a charge transfer insulator. Now again, when you go to realistic substances, you have the full degeneracy of the D bands. You no longer have a single band. In many cases, it's possible to single out a band like in the high TC superconductors based on a crystal field, but in general, you have to deal with the full multiplet U. And this, it turns out, can be completely quantified in terms of three parameters. One is F0, which is the monopole part, and F2 and F4, which are the higher multipole parts of this Coulomb interaction. Now, this monopole part is strongly screened from the atomic value in the solid because it's easy to screen charge, but these are not so easily screened. So the Hubbard U in this kind of a multiplet theory is defined in this way, where the major contribution you should note is the monopole term. Now, on the other hand, the Hund's coupling, which you're also familiar with, is entirely defined in terms of these higher order multipoles, where the charge at the site is not varying, but you're varying the relative occupancy of various spin orbitals. That is not so much screened by the by solid state or other effects. So to show this, I'm showing you some results from calculations of atomic Hartree-Fock calculations, where the U, you'll see this F0 value is very, very large. So the U calculated from such atomic calculations is horribly large, of the order of 17, see, it's 20 to 30 electron volts. On the other hand, the Hund's coupling is of the order of 1 to 1.5 electron volts, which people in the field would realize is not so unreasonable, whereas this is unreasonable. Unreasonable because if you go to an experimental, calculation of U from based on fittings to core level photoemission or a direct measurement between XPS and BIS, you would find this U in the solid, the monopole part, is only 4 to 10 electron volts. So how the hell is this huge reduction taking place? On the other hand, it's known in manganites, for example, that the JH is of the order of 1 or 0.75 electron volts, which is reasonable compared to this. Now, the way to do this is actually configuration interaction. So one way could be Coulomb scattering between various levels in the atom itself, which gives rise to, on the other would be in mixing of atomic orbitals with surrounding ligand orbitals. In both cases, what it does is it mixes the d orbital with other orbitals, giving you a larger radial extent of the d orbitals. I showed you that the radial extent is small, that crowds the 10 electrons in a very limited amount of space, giving rise to a large U. In this case, these can extend the range of that, okay? Okay, now I come to the main topic here, so which is this based mainly on the second interatomic configuration mixing. It's called the Bond-polarizability mechanism. Let's start with this. Let's take this transition metal atom with d levels in an octahedral crystal field. So as many of you know, or even if you don't know, just accept it splits into an EG and a T2G, which is twofold and threefold degenerate respectively, and the gap is called 10 dq. Okay. Now let's say the T2G levels are all filled. This is a very no spin, very heuristic picture to give you the basic idea about the mechanism. Now the oxygen is down below here. Let's take a single level. Oxygen 2p is filled in this system. Now the delta, as you saw from the previous, this here, it's of the order of 4 to 7 electron volts. We'll start with that value. So this is the energy of the neutral configuration. So there are 3 configurations involved in the definition of the Hubbard U, right? So like I showed here, n plus 1, n minus 1, and the neutral. Okay, now let's do the electron addition spectrum. Let's add an electron here. So now what happens is, so we will assume delta is still this reasonable value, but d, the UDD is of the atomic kind of value, and see how it renormalizes. So this is 20 to 30 electron volts. So the delta plus now becomes delta plus UDD because of this definition. You have an extra electron here that creates an extra repulsion UDD. So this is delta plus is 24 to 37 electron volts. And remember, delta is the energy required to promote an electron from the ligand to the transition metal. So this is enormous. Of course, things would like to backflow here, but phase space restrictions, there's nothing left here, no space. On the other hand, let's look at the electron removal spectrum, create a hole in the T2G. And now if you take out an electron here, what happens is the other way around. Delta minus now is delta minus UDD. And because this guy is so much larger compared to this in the atomic limit, this becomes negative. So what happens is now the oxygen is placed effectively higher up as far as energies are concerned. And so the energy efficient thing to do would be to sooner replace this hole here by a hole on the oxygen. And the hybridization with the EG levels is better, so that lands up here, okay? So then immediately you see from here that removing an electron from the transition metals effectively looks like removing it from the oxygen orbitals. So to a 0th approximation, UDD renormalizes to delta. But if this were the case alone, there would be no distinction between Mott Hubbard and charge transfer insulators. So this is further modified by the situation of enormous hoppings between so this was in the ionic limit completely, these things. So now you can switch on the hopping between the EG and the symmetry adapted oxygen orbitals around it. So this hopping is quite large, √3 times PD sigma. So these also have EG symmetry. You can build symmetry adapted orbitals. PD sigma itself in the titanates is 2.5 electron volts. So this is quite large. Moreover, depending on the number of channels that are empty here, this hopping renormalizes to √n times this hopping. So remember, and that can go to as large as 10 electron volts in the titanates. So the important thing to note here is this is very large. It will significantly modify this value of delta, and it depends on √n, okay? So which means that if I were to have a phase transition in which the relative occupancy of the T2G and the EG change, blocking some of these channels or unblocking some of these channels, you would see a significant change in the U. You would expect to see that. So to model that, such a transition, which is thermally driven, a rare one, is the spin state transition in cobaltates. So here, as I said, cobalt, which has 6 electrons, 3 plus, is surrounded by 6 oxygens in an octahedral symmetry, and this is how the levels split. Now, it's well known from experiments in this temperature range, cobalt is mostly low spin, meaning the crystal field splitting is large, the bond length is small. This splitting is large because of large hybridization, anti-bonding, bonding kind of splitting. So everything, all 6 electrons end up here. This is a singlet state, S equal to 0 singlet state, okay? Now here, what it wins against is the Hund's coupling JH that would rather have things pointing parallelly. And that state comes up as you increase the temperature, bond lengths increase, the hopping decreases, so the splitting becomes smaller. Now it's more favorable to do this rather than this, and you have a spin 2 state. So the low spin to high spin transition as a function of temperature is going from the singlet to the S equal to 2 state, okay? To model this, what we do is we take all of these orbitals here, the T2G and the EG, have the full multiplet Coulomb interaction on them, have the symmetry adapted oxygen orbitals, and have hoppings between them. So these 3 are the on-site energy terms. This is the hopping between the symmetry adapted oxygen and the EG only of the transition metal, the cobalt atom. And these are the detailed multiplet interactions that you can have, okay? So the effective U is calculated by taking these energy differences. So what you do is you do an n plus 1, n is 6. So you do it for 6, 5, and 7 electrons. This calculation, do a diagonalization calculation, which we do in a spin symmetry adapted basis, where the atomic spins at the bond spin are good quantum numbers, and then take this difference. So we have to keep repeating this calculation for various values of parameters. And the other thing is, you need to also root out all excitonic effects. So you do this calculation, I need just a couple of minutes. So where you do it for finite UDD, F0DD, which is the monopole part in which we are interested, and take out the value of U effective where the monopole part is 0. Okay, so since I don't have too much time, you should look at the green curve here. See, this is my effective oxygen and EG hopping. So I can say when this increases, temperature decreases. So temperature is shown in the opposite direction. As you go to higher and higher hopping, here you start first with U. This is the U real value, you should concentrate on that, which is larger than my delta used in the calculation. So this is the charge transfer regime that I defined. Then slowly as you increase this hopping or equivalently decrease temperature, this goes through a transition and drops down to a much smaller value. Here, of course, U is much smaller than delta, much larger than, smaller than delta. So this is my classic Mott Hubbard regime, which are like the early transition metals. These are like the late transition metals. So if you look at the percentage character of the eigenstates, because this is an exact diagonalization, I have my states. So you will see here it's spin 2. So this is my high spin state, and this is my low spin. But here you not only have the atomic high spin and atomic low spin states, but you also have, for example, this state when your spin is low, so which is like a Zhang-Rice singlet formed out of a hole on the oxygen and an electron on the extra electron on the cobalt EG, okay? And however, we don't find, for the people who are experts, we don't find the intermediate spin state that was proposed at some point. And you will see when this transition takes place, the value of the spin here is something like 0.25, okay? For both these, and these 0.25 actually form a very correlated singlet state, giving you the net singlet. Okay, so what we see here is along with the spin state transition, which changes relative occupancy of T2G and EG levels, you have this change large change in U that is observed in experiments, also going through this crossover from one kind of insulating state to another. So this also sort of explains why early transition metals, which have no electrons in the EG, have a smaller value of U and hence a Mott Hubbard insulators, and the other way around for later transition metals. Okay, and okay, thank you for your patience.